Okay, so we're recording right now, and let me go ahead and screen share again. Okay. All right, so you should be good now, right? Everybody sees up here where it says compound probability, right?
Yes.
Okay, so let's go ahead and do this. And so let's go to the compound probability. And remember, you can get to these either from just right here, or you can scroll down to this third module and click on it. So compound probability, you're going to see words like or, probably something or something happening, or you might see the word and, probably a something and something happening. So these are key words to look for on compound probability. Is a word like or. That means this can happen or that can happen, you know, this or that. So you want to count, make sure you count both of those, but don't count any duplicates. The word and, like if you say, what's the probability you're in this course and another course, you have to be in both to be counted. And then another word is given. So given restricts the number of people you're saying, like, what's the probability I randomly pick somebody from this class, given that the group of people that I'm dealing with are just males or something like that. So that restricts the number of people that you're dealing with. So let's go ahead, and you got links here on this homework for some material also besides the links. And I think there's also video links inside of the textbook links that I have here. So I'll go ahead and resume this. So I'll just go through the questions, and some are pretty similar questions that I'll skip after we do at least one or two similar to it. So in problem one, it says you roll a fair six-sided die twice, okay? Find the probability of rolling a 1 the first time. So I'll write it this way: the probability of rolling a 1 the first time and hello?
I'm sorry.
And a number greater than 5, I'll write it this way, just greater than 5 the second time. Okay, so let's get these. First one, these are independent of each other. The one die doesn't affect the other. So the probability of a 1 on a die is 1 out of 6. There's 6 sides. Now, the probability of a number on a die being greater than 5 is also 1 out of 6, because there's only one number that's greater than 5, and that's 6. So there's only one successful roll that can be greater than 5. You can't count 5 because 5 is not greater than 5. So the probability of rolling a die and getting a number greater than 5 is 1 out of 6. And since these are independent of each other, which means the result of one doesn't affect the other, you just multiply these together. So 1 times 1 is 1, and 6 times 6 is 36. And that would be the answer to that problem. And I tell you what, maybe just to get started, let's do we'll type it in exactly like that. I would recommend just if it gives you the equation editor, type it in as a fraction because it's more exact. But I'll tell you what, let's get a similar question on this. So here's problem number 1 a second time, just for practice. It says you roll a fair-sided, six-sided die twice. Find the probability of rolling a 4. I'll just write it this way: probability of rolling a 4, and what else are you doing? Well, and a number greater than 1 the second time. So some number greater than 1. So the probability you roll a 4, all 6 numbers on a die have the same probability coming up if it's a fair die. Any one of those 6 numbers have a 1 out of 6 chance of showing up. So the probability that you roll a 4 is just like the probability you roll a 1. It's 1 out of 6. The and here means that we need both things to happen. So to get both of these things to happen, we're going to need to multiply these together. Okay. Okay. So then how many numbers are greater than 1 on a die? Well, you got the 2, 3, 4, 5, and 6. There's 5 of them. So that would be 5 out of 6. And then you just multiply these straight across. 1 times 5 is 5. 6 times 6 is 36. So that's the idea on that problem there, how you do it. Okay, on problem 2, it says a poll was taken of 11,781 working adults age 40 to 70 to determine the level of education. The participants were classified by gender and their level of education. The results are shown below. So you can see you got your education level, high school or less, bachelor's, master's, PhD, and here's the total amount for male, female, and here's your grand total right here. And on part A, let's go down here to do part A. So on problem number 2, part A, it says, what is the probability that the selected person is male given that he has a master's degree? So let me write this out. Probability of male. Now, you don't have to know this little symbol here, but this little symbol, a slash mark, means given. It means it's out of what we're talking about here. Given that on this problem here, it says, given that he has a master's degree. So I'll put, since male is already an M, I don't want to use another M for master's degree, so I'll just write that out. So this is what it's out of. So the denominator on this problem is not going to be the grand total of 11,781. The denominator is what it's out of. And this means it's out of those people that have a master's degree. And the total number of people that have a master's degree, you can just go straight across here and you see that's 781. Now, how many of that 781 are male? Well, if you back that up on that line going across, you can see 384 of them are male, 384. And really that's it to that part. And you'll see more of those. That's one of those key words I had at the top, given or out of, same type of thing. 384 out of 781. And we'll do all these parts before we submit it. And then part B says, what is the probability that the selected person does not have a master's degree? So I'll say it this way, no masters, okay, does not have a master's degree, given that they're male. So given that they're male. So this time it's going to be out of those that are male. Well, how many are male? Well, 6,490. 6,490. Now, this doesn't say how many of them have a master's. This says how many of them don't have a master's degree. So I'll just add those up here on the top. So that means, let's see here. So of these males, how many don't have a master's degree? Well, these 2,143 don't, because they only have either a high school degree or less. Same way with these 3,897, because they have a bachelor's degree. And on this problem, I don't know if they're saying as their highest degree, but that's what they're talking about here, the highest degree. So people with a PhDs, their highest degree is not their master's degree. So we add those on. The only ones we don't add on are those that have the master's degree. Why? Because we want those that don't have a master's. So at that point, that's your answer right there. And you can type it in just like that. So we could say, okay, give me a fraction. And the top's going to be all this stuff that I have parentheses around, 2143 plus the 3897 plus the 66. And all that is over the total amount, 6490. Now, the only other way of doing this is this. You could say, and maybe this might be a little bit quicker typing, that's about it. It's out of the 6490, out of all your males. And how many of those don't have a master's degree? Well, all of them, except for the 384 that have a master's degree. Okay, so if you do this, you'll get exactly the same thing as what we have right there. Okay, let's check out part C of this problem. This problem, part C says, what is the probability that the selected person is female? So probably a female, given that they have a bachelor's degree. So I'll just put a B here for bachelor's degree. So the denominator is the total number of people that have a bachelor's degree, which you can see up here is 6,244. And how many of those are female? Well, if you look across, 2,347. And that's what you would type into right there. I'll do it real quick here for you. 2,347 out of the 6,244. And let's go down here at the bottom, get the last one. So on part D, it says, what is the probability that the selected person has a PhD? So I'll just do this, probability of PhD given female. So does somebody want to tell me what fraction that would be? Here on this last one, I'll let you guys see if you can get this one. Probably a PhD given female. How about this? What would the denominator be?
Would it be 113?
Let's see. It would be out of the females. No, it's not 113. No, that would be if it was given PhD. See this?
Oh,
Okay, so
okay.
it's going to be what? What do you think?
47?
No. Okay. Look at the previous one. Given bachelor's, what was the? Where did the 6,244 come from? Well, it came from the total number of bachelors. See. So this one.
But,
go ahead.
so I don't think I get it then with the how you found female then. Like how do you find female
Okay.
without
So are we trying, you know that we're looking for the total amount of females, right? For the denominator. Mm-hmm. So do you see where the total amount of females are in this table?
5291?
Yep, that's it. Now,
okay.
So that's always the bottom number comes from the what's given. It's out of, we're told, out of just the females here, given that the person is female. So now of those 5,291, how many of them have a PhD?
That's the 113. Oh wait, no, the female PhD?
Mm-hmm.
47.
Boom, that's it. So yeah, just you can get it. Yep, you got it. So 5291. And then let's go ahead and submit this. Yep. Okay, moving on to problem 3. Let's take a look at it here. So on 3, it says, here's a little table with same type of thing. This is gender here and a person's grade here. And it says, if one person is chosen random on part A, it says, find the probability that the student got an A. Well, it didn't say given or anything. This is just a straight probability. So how many A's are there in this table? Folks, or how many A's?
21.
And that would be out of what?
72.
Boom, that's it. Let's go to part B on this. And on part B, it says, find the probability that the student was male and, so I'm going to write it this way, probability of male and keyword here, and you see how they even capitalized it there to focus on that. Probably the student was male and got a C. Now this is not given or anything like this, but here's a key word. So we don't restrict the number of people we're dealing with because it didn't say out of just your females or given that the person's a male or anything like that. So it's still going to be out of 72. Nothing changes with that. But how many of these students are male and got a C? Does somebody want to try to answer that? How many of these students are male and got a C? Somebody want to try that one? In this table, how many people are male and got a C?
Okay, so male, so 31 over 18?
Well, these 31 right here, are they male? Yes. Did all 31 of them get a C?
No.
No. So we need only those that are male and got a C.
So it's 18.
That's it. 18 out of 72. Now, notice that the 72 is still 72. It's not given or anything like that, like you're just dealing with males or females like previously ones. See up here, all these previous ones, it was like given female, given bachelor's, given male, given that they had a master's degree. That's not what we're dealing with on this problem. We're dealing with the other keywords, which are the ands and the ors. See, we did the givens, and now we're getting to the ors and the ands. So when you say and, they have to have both. The person has to be male and they got a C. How many are male and got a C? 18. So what's the probability of randomly selecting one of these 18 people out of the 72 people we have total? 18 out of 72. So that would be the answer to part A, 18 out of 72. And if it said reduce the fraction, I would have had to, but it doesn't say it has to be reduced or anything like that. On that is the answer to part B. I didn't put in the answer to part A. Part B was 18 out of 72. I'll put in the answer for part A, which is 21 out of 72. That was just a straight probability of A. Now, this one's even harder here. On part C, it says find the probability that the student was male or got a B. So pay attention to that word male. Not the word male, the word or. That's the key word right there. Probably that the student was male or got a C. So there's nothing about given that the student is female or given that the student got a C. The word given or out of is not in there. It's just out of all the students. So the bottom number is definitely 72. Okay, not a word given on part C. So the bottom number is 72, the grand total. Now let's get, you guys help me out here, get the total number of people that are male or got a C grade. So we can do it in pieces, or you can tell me the total answer if you like, but we could do it in pieces. That's how I generally do this. So what I do is I get the total number of males. So what's the total number of males we're dealing with here in this table?
31.
Right. Now what I do after this is I say, okay, what's the total number of people that got a C?
18.
Yeah, no, that's not the total number of people that got a C.
Oh, 27.
Now, here's the tricky part. Did any of these people, did the 31 males or the 27 people that got C's, were any of those people counted twice? You don't want to count people twice. Every person should be counted once. Did any of these people get counted twice?
Yes.
Yes. Yes. So
Yeah.
we have to subtract those people off because they were already counted twice. They got counted once because they're male, and they got counted again because they have a C. So how many people got counted twice?
18.
Boom. Yeah, very good. Now, let me show you that on this picture up here on this graph. So we count up all the males. That was the 6. What made up this 31 people here? See, the 31 people right there was made up of the 6, the 7, and the 18. What made up the 27 people that got the C's? Well, that was the 18 and the 9. See, these. So these 18 people that are male are counted once because they're male, and they got counted again because they got a C. You can't count people twice. You want to get the probability, everybody has to be counted that you want to get counted. Everybody has to get counted once. So since they were counted once because they're male and once because they're got a C grade, we have to subtract them off so that each person is only counted once. So you don't have to do the arithmetic. We can just type it in there. But notice that the or is tougher than the and. It's a little bit complicated there. So I'll type this in. It's 31 plus 27 minus 18. And all that is out of 72. Okay, so that's that one there. And then on part D, if you look at part D, the word given does show up on part D. So let's take a look at D. So it says, if one student is chosen at random, find the probability that the student got a C. So I'll just write it this way, probability that the student got a C, given the student is male. Okay, remember this means right there, it's given the student is male. That's your bottom number. It's out of the males. How many males do we have? 31. See, that's the given that makes the denominator change. Given that the student is male, how many of them got a C? 18. So it'd be 18 out of 31 right there. Okay. So we'll type that in. And we should be good. Oop. I must have done an arithmetic mistake here. Let's check this one again. So find the probability that the student is male. Oh, it says B. Daggone it. I wrote down C. So I tell you what, let's do the problem again for practice. So for practice here. So back to problem C. It says the probability the student was male or got a B. Well, it's still out of the 72. We count up all those students that got a that are male, that's 31. Then we count up all the students that got a B, that's 24. And you guys tell me, how many people were counted twice?
The males.
Oh,
Oh, how many?
yeah.
7.
That's right. So you subtract the 7. So again, if you're having trouble with that, you counted up all the males. That was the 6, the 7, and the 18 that give you a total of 31, all those. Then you counted up all your Bs. That's the 7 again, plus the 17, which got you the 24. But the 7 got counted once because they're male, and they got counted again because they got a B. Got to subtract them off because they were counted twice. When you subtract them off, count them all twice. When you subtract them off, then they're only counted once. So the right answer is actually this fraction at 31 plus 24 minus 7, and all that stuff is over the 72. Okay. All right, so that's good stuff. And let's see what we got here. So this one, if you have a whole bunch of data, notice there's no table, but they break it into a table worth of information. So I would recommend on this problem, or any problem like this, that you have, you know, something that you could make up a table for to keep it straight, make up a table for it. It's really hard to do these problems unless you make up a table. So in problem 4, let's keep track of it. You'll see what I mean. You basically have 2 variables going on, whether the student is male or female, and also you have whether they speak Spanish or not. So let's keep track of this stuff. We'll read it through first, I guess, here. So I'm just trying to make up a little table here for us. So this one says, suppose a math class contains 37 students. There are 19 females, 4 of whom speak Spanish. So there's some females and there's some males. Some speak Spanish and some, I'll put NS for no Spanish. Okay, and we'll keep track of the totals. We have to get the totals to know what it's out of to get these probabilities. So let's keep the totals on both areas here. So there's 37 students. That's my grand total right here. There are 19 females. Total number of females, 19. 4 of whom speak Spanish. So 4 of these speak Spanish. And there's 18 males. Boom, 18 males. 6 speak Spanish. 6 right here. Now what we can do, just in case we need it, and we will, is we can complete the table. So the total number of Spanish people, Spanish speakers would be 4 plus 6 is 10. We can get how many don't speak Spanish by subtracting how many speak Spanish from the total. So 19 females total, 4 speak Spanish. 19 minus 4 means 15 don't speak Spanish. Same way here, 18 males total, 6 speak Spanish. 18 minus 6 is 12 that don't speak Spanish. And we can get the total here. The number of people that don't speak Spanish is 27. Now we can go through these parts. Probably should label them A, B.
Professor,
Yeah,
I'm sorry. You
That's
just went
okay.
a little fast.
that's okay.
How did you do that again?
Okay, well, I
Yeah,
read, okay, reading the problem, they gave you the total, and they gave you the total, like females and 4, there's 19 females, 4 speak Spanish, 18 males, 6 speak Spanish. Then I got the totals here, but just adding these up, 4 and 6 is 10. And then here, the way I got the 15 is there was 19 total. I subtract off the 4 that speak Spanish. That means 15 don't speak Spanish. And I did the same thing here. You okay there?
Where did you get the 15 from?
19 minus 4.
Okay.
Right there. There was 19 total, 4 spoke Spanish. Okay. Right here, there were 19 females, 4 spoke Spanish. They didn't tell you how many didn't. You either do.
Okay, I didn't read that right. Okay.
Okay. And then, okay, I'll call this part A, part 1 or whatever. It says, what is the probability that a randomly selected student speaks Spanish? So I'll write it this way. Probably that they speak Spanish, given that the student is female. Okay. So how many females do we have? 19. How many of them speak Spanish? 4. So that would be the answer to part A. And that was actually given in the problem there. There were 19 females, 4 whom speak Spanish. And that's what they wanted on part 1. Part 2 says, what is the probability that a randomly selected student does not speak Spanish? Okay, I'll call it this, no Spanish, given that the student is male. Okay, so it's out of the males. How many males do we have here? 18. And how many of them don't speak Spanish? 12. See, this is where I'm using my table now. See, I'm using the table over there. First one I could have got without using the table. That's true. But for some of these, it's really difficult if you don't have a table made up. Okay. So what's the probability that a person does not speak Spanish given that they're male? So it's out of the males, 18 of them. How many don't speak Spanish? 12. I'll do it right there. Let's check out the third part. What percent of Spanish speaking students are male? It's just that. What percent? Oh, what percent of? See, that's confusing. It's out of. Watch out for that word there. Here, let me go up here at the top. Watch out for the word given, which is the same as saying out of or of. What percentage of these particular types of students, whether they speak Spanish or they're female or whatever they're talking about there. So of and given or out of, they don't even have what percentage of this group. So let's go back down here. So again, the third part says what percent of Spanish speaking students. So it's out of your Spanish speaking students are male. So that tells me that it's out of the Spanish speaking students, which there's a total of 10 of them. How many of these 10 are male? 6. Okay. It's not hard to do in the fractions. You just get them off the table, but it's being very careful readers to know, oh, okay, what does this mean? What percent of Spanish? It means it's out of just your Spanish speaking students. And then the fourth part to this says, if someone does not speak Spanish, what is the probability that they are female? So this is the hardest part. I'm going to let you guys try to tell me what I would write here. You could tell me this, or you could tell me either the top part, the numerator, or the denominator of the fraction for part 4 here. So again, it says, if someone does not speak Spanish, what is the probability they are female? So you can tell me any part of this problem, either what you want here, or if you don't like this way of writing it, if you just know what goes here.
15.
Okay, 15, so you give me these pieces here. Does the 15 go on the top or on the bottom?
I think it goes on top.
That's good. That's good. 15. What goes on the bottom?
Um, 27.
Yeah, that's it. So this one didn't say of, and it didn't say given. It said, but it means the same thing right here. It says, if someone does not speak Spanish. So we're saying that we're dealing with somebody that does not speak Spanish. How many people don't speak Spanish in this table? 27. That's what it's out of. So if I had to say what this is out of right here, it's out of those people that do not speak Spanish, no Spanish. And then it says, what is the probability that they are female? Of these people that do not speak Spanish, there are 15 that are female. Boom, that's it. Oh, here, I'll do that with a letter there, since I tell you where the number came from. That 15 came from those that are female, given that the person does not speak Spanish. And that's it. And I'm not going to type all those in and waste your time with me typing them in. Let's go ahead and go on to the next problem here. So on this next one, you won't see the word and or too much. You might see or occasionally, but like if somebody says, what's the probability of me selecting a, I don't know, a female nursing student? Then if you see two words written in a row, female nursing student, that means they got to be both. They got to be female.
Water.
Say
Please.
again. Say again. Kelvin?
Oh, no, never mind. I'm good.
Okay. Okay. So you might, well, let's go ahead and do it here with question 5. So here on 5, it says about M&Ms, you know, the candy M&Ms. So it tells you what percentage are brown, yellow, red, blue, orange, and green. And let me tell you what, these numbers are assumed to be true for the billions of M&Ms, if not trillion of M&Ms that are made. Okay. So when one little M&M is taken out, there's still, out of this huge amount of M&Ms, the probability does not really change hardly at all, a minuscule amount. So when you take one out, there's still millions and millions of M&Ms there, and there's still 12% that are brown. They're being made all the time. They're eaten all the time, especially with Halloween around the corner here. So you have these percentages. And then on part A, it says, compute the probability that a randomly selected peanut M&M is not red. So I don't know how you want to say that. I'll just say not red. So not red, how many are, look, we can do it one of two ways. We can add up the percentages that are not red. Like we could add up the probability of brown plus the probability of yellow. And I'll abbreviate some of these, plus the probability of blue, plus the probability of green. We could add all these up, plus the probability of, what do we have left? Orange. I missed out orange there. We could add up them all except for red. You can do it that way if you want to. The other way of getting the probability that you get one that is not red is take 1 minus the probability that they are red, because that 1 right there stands for 100%. So the probability that you get one that's not red is just take 100%, because this is all of them right here, and just subtract off those 12% right there, that 12% that are red. So just subtracting off that 12%. And if I do that, I get 88%. Now, unless they give a percent sign there, type that in as a decimal. So 88% is the same as 0.88. So for me to type in a percent, I need to see a percent sign, or I need for them to tell me specifically, type it in as a percent. So if they don't tell you that, just type it in as a decimal. So in part B says, compute the probability that a randomly selected peanut M&M is red or green. So we want the probability it is red or green. So it could be either way. So let's get the red ones. which there's 12%. So I take the probability of red and I'm going to add on the probability of green. So 12%, I'll just say 0.12, right? 12% is the same as 0.12. That's the percentage that are red, and the percentage that are green are 15%. Now, earlier when we had an or, we had to watch out, and we'll check it here, watch out that we don't count somebody twice or count some M&M twice, like we did with female and bachelors or whatever that problem was a little bit ago. A grade, I think it was male and B. If you do male or B, some people got counted because they were male, and some got counted because they were B, and some of those folks got counted twice. Well, in this one, we don't have to worry about counting any twice because there's no such thing as a red-green M&M, one that gets counted once because it's red and it's also green on the other side or something like that. So there's nothing to worry about with this. This is an easier problem, so you just add these up and you get 0.27, and that would be the answer to part B. On part C, and I'll go ahead and type in the previous answer here, which is 0.27. But on part C, it says compute the probability that the two randomly selected M&Ms are both brown. So we want the probability of brown and brown. So the probability that the first one is brown is 12%. The probability that the next one is brown is also 12%. Now look, the key word here is and. It's not an or. We don't add these. If you look back to an earlier problem, like the ones we did with the dice, it's the very first problem. See, we had an and in there. And what did we do with these two fractions? We multiplied them, right? 1/6 times 1/6. See, an and, we multiplied. Then we got into other ones that were given, and we had a table one where we could look up the value. But down here, see, an and, you multiply. So we're going to multiply these together. And so it's 0.012 times another 0.12. And I'm not sure what you get when you multiply those together in my head. So I'm just going to do 0.12. And what I can say instead of times another one is just faster for me to do that caret up and a little 2 for saying squared. And that's what you get right there. So remember, multiply those together. It's just like the dice. 1 out of 6 and another 1 out of 6. That's because with the dice, there's 36 possibilities for those, 6 for the one die, 6 for the other, and you could list all the ways they occur, just like we did the other day with the 2 coins. There's 2 options for this coin, 2 options for this coin, 2 options for this coin. 2 times 2 times 2, there's 8 ways those 3 coins could land. So that's why you multiply. So let's go to D. And D says if you randomly select 2 peanut M&Ms, compute the probability that neither of them are yellow. So we want the probability of not yellow and not yellow. So that NY here stands for not yellow. So let's get this. So first of all, let me do on the side here, what's the probability that an M&M is yellow? Well, up there, the probability that it's yellow is given to be 15%. It's given to us at the top of the problem. So therefore, the probability that an M&M is not yellow, we just take 1 minus that. 1 minus 0.15, which is 0.85. So if that's the probability of not yellow, then the probability of not yellow and another not yellow is 0.85 times another 0.85. And the easiest way to type this in is just say 0.85 squared. And that's how I'll type that one in.
Professor, I have a question.
Yeah.
So for letter C, on yours it says are both brown, and on mine it says are all brown. Are they does all both mean the same thing?
Yeah,
no?
but you must be dealing with 3 or more M&Ms. How many do you have?
1, 2, 3, 4, 5, 6.
Does it say 6 somewhere along that problem?
It just say, oh, it says 3.
3. There you go. So see,
So
yours
it's
is
okay.
yeah. So yours is going to be like mine's 0.12 squared for part C. Yours is. Did your percentages stay the same or not?
Yes, they're the same as yours.
Oh, okay. So if it's whatever color you're dealing with, raised to the 3rd power then on yours.
Okay.
Okay. And then I'll go to E here. And then E says, if you randomly select 2 peanut M&Ms, compute the probability that at least one is yellow. So mine's dealing with 2 again. Probably that, I'll write it out here, at least 1 yellow out of 2. Okay. So this is a tough one here. Okay, this is a tough one. At least 1 is yellow. Well, look, this is out of 2. Mine is out of 2. And like you heard, I think, I forget who was talking to me, if it was Wendy or Paris or someone else, but she might be dealing, or you might be dealing with 3, 4, or 5 of these M&Ms. So the way I'm going to show you is really the best way of doing this, because if you do it a straightforward way, you get so many possibilities, it's hard to deal with. So I'll say it this way. Mine says it's out of 2, right? Out of 2 M&Ms, what's the probability of at least 1? So at least 1, what does that mean? At least 1 means it could be 1 or 2. See, if you were dealing with 3 M&Ms and you said at least 1, that means 1 or 2 or 3. At least, at the words at least means that many or more. You have to be at least 18 to vote. What does that mean? You could be 18 or older, okay? At least means that much or more. So at least 1 for me means 1 or 2. If you're a person that has 4 M&Ms on your problem, at least 1 means 1 or 2 or 3 or 4. Well, that's a real pain to do all those probabilities. So the only thing that it can't be when you see something like at least 1, it means this: at least 1. We know that means 1 or more, but here's what we know it means. It also means this: all but none. We want either 1, we want 2, we want 3, but we don't want none. We got to have some. Okay, that's what that means. At least 1 means we got to have some. Got to have 1 or 2 or 3 or 4. Can't have 0. Okay, I'll write it that way. Can't have none. Okay, so what we'll do is get the probability of none and then just take 1 minus that, and that will give us what we're looking for. So it's kind of confusing. I'll talk it over again when we're through it, but let's go ahead and get the arithmetic for it. But the idea is, again, at least 1 means 1 or more. So we're going to get the opposite of that. The opposite of at least 1, okay, it's called the compound event of that, just means the opposite, what are we not getting? We don't want to have none. So I'll get that one and take 1 minus it. So let's get the probability of 0. So the probability of none of them yellow, would be this. The probability of no yellow on 2 marbles means not yellow and not yellow. So the probability of not yellow and not yellow, we got that right up above. That was at 0.85 squared. That was our answer to part D. Part D. Our answer, at least 1, probably of at least 1, is going to be 1 minus that answer. So that's tough. And you may not get this in class today, this one, but when you get to this one on your own, you can refer to this video or the written example And the written example explains it just like I did. Like, who was the one that said they talked a second ago and said they had 3 marbles? Like, they asked about part C.
That was Paris, and I had 5.
That was,
Oh wait,
that was Paris?
which one? Yeah, for part. Oh yeah, for part 3, I did have 3 marbles.
Okay, so you would do yours, Paris, the same way. You get your answer to part D, whatever it is, make sure it's right, you know. But if part D is right, all you have to do to get the answer to part E is take 1 minus your answer to part D. So in general, you do 1 minus your answer to part D. Okay, so see, here's my answer to part D. My answer to part E is 1 minus that stuff, 0.85 squared. And the reason is because at least 1 means 1 or more. So if we get the probability of none, then we just do 1 minus that. That's it. So that's how you do that problem. I know it's a weird one, especially the last part's kind of tough. But okay, so now back to shorter problems. And we just did one of the hardest problems there. So on problem number 6, it says suppose a jar contains 7 red marbles and 31 blue. So we'll keep track. 7 red, 31 blue. And it says if you reach into a jar and pull out 2 marbles at random at the same time, find the probability that both are red. Okay, so this is getting you ready for something here. Find the probability that you got a red one and another red one. Okay. Now, unlike the M&M problems, remember the M&M problem, where was it? Right here with these percentages? That's because there's billions of M&Ms out there. And when you take one M&M out, that 12, let's say you select one of the billions of M&Ms out there, and it's a brown one. That doesn't lower that percentage from 12% to 11% or anything like that. They're being made all the time. You got all, billions of M&Ms. But now on problem 6, you don't have a billion number of marbles. You have a really small number of marbles that we need to deal with. So watch this problem. It's a little bit different. So,
Planet Fitness to use the bathroom.
okay, somebody turned on their mic here. So let me see. And I'm not sure how to mute people here. I can ask them to mute. Let's see. Okay, I think we're okay. I don't know. Okay, so the probability that the first one is red. Let's get the total here. The total is, we got 38 marbles total. Now the probability that the first one is red is 7 out of 38. They got that marble in their hand. They maybe didn't pull it out, but at some point you got to grab a marble. So 7 out of the 38 are red. Once you get that marble in your hand, what's the probability that the next one is red? So I'll let you guys answer that one. Anybody want to try that? Hello.
6.
Yeah. Out of what?
37.
That's it. That's it. So, yeah, because what happens is when you have that one marble in your hand, the only way you're going to get 2 red ones is that the first one is red. So the first one you had, it had to be red. So the second one, then there's 6 marbles left that are red. And since you already have a marble, it knocks the number of marbles down from 38 down to 37. So in general, what we did is the number of red out of the total Then when one is gone, then it was the number of red minus 1 over total minus 1, because we had that one red marble in our hand. And it would do the same if we had 3 marbles we selected. It'd be 7 out of 38 times 6 out of 37 times 5 out of 36, because we keep on grabbing another one. So I would just type that in as I have it there, the 7, with 2 fractions multiplied together. 7 out of 38 times, and I'll just say times like that. And I think even if you don't put the times sign in there, it knows it, and that's out of 37. And if we submit that, it should be right. Let's go to 7 here. So on 7, it says a jar contains 5 pennies, 7 nickels, and 5 dimes. So let's keep track of those. 5 pennies, 7 nickels, and 5 dimes, and get the total amount. So the total number of coins that we're dealing with, not the total amount of money, just the total number of coin is 17 coins. Okay. And it says find the probability of getting 10 cents on 2 coins. Well, the only way that you can get 10 cents on 2 coins is they both have to be nickels. So it takes us back to problem number 6. So the probability that both are nickels is, how many nickels do we have? We have 7 nickels out of the total number of coins, 17. Then once we have that 1 nickel, that takes us down to 6 nickels out of the total number of coins is 16. And that would be the answer to part A. Part B, how can you get 11 cents? 11 cents on 2 coins. On 2 coins, that's what the problem says, is 2 coins total. So there's 2 ways to get 11 cents. It could be that the first is a dime and the second is a penny, or it could be that the first is a penny, probably the first is a penny and the second is a dime. You might say, aren't they the same? No, you have to look at them like, if you flip 2 coins, it could be heads, tails, or tails, heads. Isn't that the same? No, there's a difference. One time, the first coin is a dime, second coin's a penny. The other time, the first is a penny, second is a dime. Both of those are options that couldn't come up. So we have to, figure both of those probabilities. So let's do this one, the probability of dime and penny. Let's do that one. So the probability that the first one is a dime, we have 5 dimes, and that's out of the 17 coins, times how many are pennies? Well, we have 5 pennies still out of the 16 coins. Now, if you did this one, probably of penny and dime, you would find out it's the same thing. So the OR tells us we have to add these together. Adding this with itself is the same as multiplying it by 2. So there was 2 options for this. That's where the 2 comes from. This 2 right here comes from the fact that there was 2 options. That's where the 2 comes from. And this comes from the same thing as we did up here. Just get the number of dimes, 5 out of 17. Now, how many pennies are there? There's still 5 pennies, but they're down to 16 coins. So that's what you would type in there for that one right there. Okay, you'll see others like that as we go through. This one is not like this. This one's a easier problem. 8 is. So let's do 8. And you'll see other ones like 7. So 7 is one of your first ones that is like that, where you have to check the different possibilities. So on 8, it says a jar contains 8 red marbles. So let's keep track of these. 8 are red, and they're numbered 1, 2, 3, 4, 5, 6, 7, 8. And there's 11 blue marbles, and they're numbered. Each one has a number on it from 1 to 11. So on part A, it says a marble is chosen at random. If you're told that the marble is red, what is the probability that it has a number 5 on it? So if you're told that it's red, so it's out of, so it's back to this given stuff, out of the fact that you're told that it's what? Red, I think here. If you're told the marble is red, so that we know that the marble is red, and we're looking for what's the probability it has a 5 on it. So if we're told it's red, we're just dealing with the red marbles. How many red marbles do we have? 8. And of those 8 red marbles, how many have a 5 on it? Just one, because each marble has a number on it. 1, 2, 3, 4, 5, 6, 7, 8. So that would be 1 out of 8. On part B, it says the first marble is replaced. So now we're dealing with all 19 marbles. And it says, and another marble is chosen. If you're told the marble has the number 1 on it, so now what we're saying is, given that it has a 1 on it, what is the probability that it's red? So what we have to do here, it's given, or it's out of the total number of marbles that have a 1 on it. Well, how many have a 1 on it? Well, 2 marbles have a 1 on it. There is a red marble with a 1 on it and a blue marble that has a 1 on it. So it's 2 of them. How many of them are red? Just 1 of them. And that would be the answer to part B. So you might have to watch these twice, or yeah, remember this video, it will be posted. So you might need to watch it for some of these confusing ones. That one actually isn't that bad when you think about it. You know, like for example, let me do a part C on this one. Okay, so before I go to number 9, here, I'll give you a part C. So let's say it said this. What's the probability the marble is, let's say, red, given that it has a 10 on it? Does anybody want to try to do that one? Because that comes up. This is a same type of thing as this second one right here. What's the probability it's red, given that it has a 10? Anybody want to try to do that one? So let me ask you this. How many of the marbles up here have a 10 on them?
1.
Just 1. And what color is that one marble that has a 10 on it?
Blue.
It's blue. So what's the probability the marble's red if it has a 10 on it?
0.
Bingo. 0 out of 1, which is 0. If it says what's the probability it's blue, given it has a 10 on it, well, there's only one marble that has a 10 on it, and that marble is blue. There's only one marble that has a 10, and it is blue. That's 1 out of 1, or a 100% chance on that. That's a weird one that comes up. Okay, let's go on up to 9. This is actually a big one here today, where we're covering 2 sections. So we'll do some from the next section here in just a little bit. So on 9, it says you have a box of chocolates that contain 15 pieces, of which 8 are solid chocolate. So let's keep track of these. 8 are, I'll just do this, solid chocolate. I'll do SC for solid chocolate. 4 are cashew. Okay, so I'll do cashew. And then 3 are cherries. I'll do CH for cherries. Okay, let's get our total. See, we did one like this already right up here with the coins, right? See, pennies, nickel, dimes, solid chocolate, cashews, cherries. So we get the total. So that's 15. And now we can answer anything with it. So let's do it. Find the probability that a probability of selecting a solid chocolate. So let's get this. Solid chocolate followed by 2 cherries. So cherry, so, and another cherry. Okay, so let's do it. So the probability that the first one is solid chocolate is 8 out of 15, right? Because there are 8 solid chocolate pieces in there and there's 15 total. Times the probability that the next one is cherry is there's still 3 cherries left, but we only have 14 pieces of chocolate. Times probably that the next one is cherry is down to 2, because we already took one of those cherries out, and it's down to 13 pieces of chocolate. And that's it. Now, that's real similar to like the nickel thing type of thing. Okay. So on part B, though, it says find the probability of selecting a solid chocolate, and 2 cherries. And you say, well, that's the same problem. But it says this, in any order. So that makes this problem more like the dime penny problem up here. Okay, you see this one with the nickel. right? Part A, that was straightforward, like the first part of this problem. But with the 11 cents, it was dime penny or penny dime. So that's the same thing you got going on down here. We have to check, we have to see how many different orders there could be of these things. So this order right here is with the solid chocolate piece being first and then the 2 cherries. So what's another order of arrangements of these 3 pieces? The first piece, instead of being solid chocolate, could be what?
Cherry, cherry, solid chocolate.
Right? And is there another way it could come up?
Cherry, solid chocolate, cherry.
And you can think as much as you want, and that's it. So there are 3 ways that this could come up. Now look, at the previous one, it was easier. There was only 2 ways, dime penny, or second way, penny dime, 2 ways. And what do? We took the answer and multiplied it by 2. So down here, what we're going to do is take our answer to the part A. We're going to take our part A answer, or just the fractions, at 8 out of 15 times the 3 out of 14 times the 2 out of 13, and multiply it by 3. Where'd the 3 come from? The 3 arrangements. This comes from the 3 arrangements of these. 3 arrangements. See, 1, 2, 3. Boom. And that's what, and I would just type it in like that. I wouldn't do it all on a calculator. I haven't used the calculator at all today. I would just type it in like that right in there. Save a lot of time. This is the same type of thing on this as we've been doing. So I know these are hard problems and they take a while, but it's the same idea of what we've done on the coin problem and also the chocolate problem. And look, we're back to more of the same. See, you're getting a lot of these type of problems and same stuff. So you see a good many of these problems. This is just a multiple choice problem. It's asking, what formula. I don't really like this problem a lot because it's asking for formulas. So I'll do this one real quick. This one, if things are independent, that's where you multiply things together. It's not this. So this is not true. If events A and B are overlapping, then the probability of A or B is equal to, you add up your 2 probabilities and you subtract off those that have been counted twice. That's what that means in terms of a formula right there. So that one's true, and everybody gets the same problem on this. So, I mean, you can just mark it down now if you want. The third one, if the probability of A is the probability that event A will occur, then the probability that event A will not occur is 1 minus that. We've done that a lot of times. So like if the probability of rains is 30%, the probability it won't rain is 70%, 1 minus that. If events A and B are independent, that means they don't influence each other. Then if the probability of event B occurring is the same, whether or not event A occurs. That's true. So coins are independent of each other. The probability that this coin lands heads is the same whether this coin lands heads or tails. That means they're independent of each other. And then 2 events are independent if they cannot occur at the same time. No, that's not true at all. You can flip 2 coins and they both land heads and they're independent of each other. So I think it's just that bit right there that are true. And I think we're pretty much through this. This is more table stuff like the early ones we did with tables. So it's not too bad, but look back with this one, see the percentage signs? They want the answers in percents on that one. And then this is still table stuff, but look, they want the answers in percents. So not a horrible thing. And then this one is a kind of a social justice problem that I put in that deals with percentages. And I'll let you guys go through that on your own where you can fill in the table on that. And this one is too. So you can go through that one. Since we can always go back to these, but let's take a look at the other homework problem that we have. And the other homework set that we have is counting techniques. So let's take a look at that and at least get us started on this. And there's a textbook link on there, plus this video will be up. And, a lot of these problems have videos or written examples linked to them. So let's go through some of these. There's a total of how many problems on this? 12 problems on this one. So if we take a look through this, we can see, let's go ahead and take a look at this on counting techniques. So I'll just label it right here. So what this is getting all the possibilities that can occur. And that's, they call it counting techniques. So on problem number 1 here, it says a computer password is required to be 8 characters long. How many passwords are possible if the password requires 2 letters? So let's keep track of it. 2 letters, these are letters right here, followed by 6 digits. 1, 2, 3, 4, 5, 6. Now read on and see if there's anything. It says where no repetition of any letter or digit is allowed. Okay, so if you don't know, there's 26 letters in the alphabet. So the choices of the first letter is 26. Now, since it says no repetition of any letter or digit is allowed, that means how many choices are there for the second letter?
25.
That's right. Because no matter what letter shows up here of the 26, it can't appear again. So there's 25 options right here. Now for these 6 digits, you were talking about single digit numbers. There's actually 10 single digit numbers, right? 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. There are 10 single digit numbers. There's 10 numbers right there. So there's 10 choices here. But no matter which one you choose here to be your first number, let's say it's a 3, there's only 9 choices left. Once you do that one, whatever it is, I'm just marking one off, there's only 8 choices left now. And once you choose that one, there's only 7. And once you choose that one, there's only 6. And once you choose that one, there's only 5 to choose from. 1, 2, 3, 4, 5. 5 numbers to choose from. What do you do with these? Just multiply them together. And I don't know an easy way for you to type that in, but it's just as easy to type it in here as it is on a calculator. So I would probably do 26 times 25 times 10 times 9 times 8 times 7 times 6 times 5. Bit of typing, but that should work there. So that's called counting techniques, where you see how many possibilities you have, and then you just multiply straight across there. Let's take a look at 2. 2 says a computer password must be 5 letters. 5 letters here, followed by 5 digits. Wow. 0 through 9, your 10 choices here, just like we had before. Now let's read this up here. It says how many different computer passwords can be made, assuming that letters and digits can be reused. So for the letters, if the first one's an A, guess what? You can do it again. So you get 26 choices for the 26 letters all the way across. It's okay if your password is A, B, A, B, A, or A, all the way across. So you have 26 choices. Same way with the digits. Your numbers here could be a 1, 2, 1, 2, 1, 1, whatever. So you can use any of the 10 digits all the way across. So the easiest way of typing this in would be use exponents. This is 26 times itself 5 times. In other words, 26 to the 5th. And this right here is 10 to the 5th. And so I'll at least type that one in. So this would be 26 to the 5th. And then times 10 to the 5th. And that should do it. And let's, I'll miss this one. I didn't type that in. But let's check it here again. How many letters it says 4. Well, let me check it here. 4 digits. So the number of digits here is 4. So that should be 4th right there. And whoa, let's see it. 5 letters followed by 4 digits. Oh, sorry, a little bit tougher here. Let me go up to the top. I think I just did the first part of this one here. Sorry. This is 26 to the 5th. One more time here, 26 to the 5th, and then times the 10 to the 5th, sorry. Okay, that we just answered part A. Let's go down to part B and get that. So this was part A. Part B says 5 letters followed by 4 or 5 digits. So nothing's changed with the letters on part B. So that's still going to be 26 to the 5th. The tough part on part B is where it says 4 or 5 digits. So the first 4 digits are easy because there's 10 choices. Now here comes the tricky part. The 5th digit. The 5th digit, this is what makes this tough. It could be there. It could be a digit. It could be 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, which is 10 choices. But it also could be blank because it says it has to have 4 or 5. So that means it's okay to just have 4 numbers and leave this one off. So there are 11 choices for this one. Those choices are 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, or blank. So that's, not 10. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, or blank. And that makes 11 choices for it. So that's a weird one there. It's like you maybe see one where it's you have 3 choices for a tie to wear, and the tie is optional. That gives you a 4th choice, which is don't wear the tie. So anyway, that's how that one works out there. And taking a look at number 3 here. So it says a bride is choosing a dress for her bridesmaids. There are 7 styles. So let's just keep track. 7 styles, 6 colors, and 2 fabrics. And how many ways can she select the bridesmaid's dress? Well, it could be a particular style, any one of these 7 times. It could be any one of these colors times. It could be any one of these 2 fabrics. See, like you could have fabric A or B, you could have color A, B, C, D, E, or F to choose from. So they could choose fabric A with color B with style C. So to get the number of options, we just multiply these together. That's all you do. Multiply these together. Okie dokie. So on this one, it's a true or false situation. So it's true or false. So a quiz consists of true or false questions. And how many ways can a student answer the quiz? Now there's 7 true or false questions, 7 true or false. So how many ways could they answer the questions? Well, here's your questions, 1, 2, 3, 4, 5, 6, 7. How many choices do they have there? 2. It's just like heads or tails. Same way here, there's 2 choices. So there's 2 choices for each one. And all we have to do is multiply these together. And again, to save time, I would just type this in as being 2 to the 7th when you type that in. It's just like if there was multiple choice problems. If there's 4 choices per problem, then it would be 4 to the 7th. So let me see if I can get down here to the bottom to, hold on here a second, get some space. So we'll take a look through these. And this is the same type of thing here. On part A, you got 5 pair of pants, 6 shirts, 8 ties, and 3 jackets. How many outfits can he wear to school? You must wear one of each. Can't go to school without your pants on. So that would be 5 times 6 times 8 times 3. But here on part B, it says how many outfits can he wear if he must wear pants, the shirt, and the jacket, but the tie is optional. Well, he has to wear one of the 5 pair of pants times he has 6 shirt options, so times 6. But for the tie, since it's optional, I'll let you guys answer this. Since the tie is optional, how many choices does he have?
9.
Boom, that's it. There's 9 options. Why? He could wear tie number 1, 2, 3, 4, 5, 6, 7, 8, or no tie at all. That's the 9th choice since it's optional. Then times the 3 jackets. For some reason, I guess he has to wear a jacket. but that's all there is to that one. This says 9 bands. So here we are on problem 6. It says 9 bands are to perform at a weekend festival. And how many different ways are there to schedule their appearance? Okay, we'll call these bands A, B, C, D, E, F, G, H, I. Okay, or you can call them 1, 2, 3, 4, 5, 6, 7, 8, 9 if you like, but I just didn't want to get any numbers confused with how we're doing this here. So we pick which band we want to appear first. So how many options do we have? 9 options. Once we choose that band, let's say we want C to open, be the first band to play. Once we choose that, then we have 8 remaining bands to choose to go on second. Then once we choose that band, we're down to 7, and you get the idea. And once we choose that one, and so on. So it's going to be 9, and the right thing to do is multiply in between here. So it's going to be 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. Now, when you go from a certain number all the way down to 1, multiplying that together, even if it was 10 or 100, all the way down, and you wouldn't want to type in 100 times 99 times 98 all the way down to 1, there's a shortcut way of writing that. And that is this, 9 with an exclamation mark. So exclamation mark, which is called factorial, means to multiply every whole number all the way down to 1 from that number. So watch, you'll see this here. If I type in 9, I guess we don't see it up there. It's not a choice up there. But if you just type in the exclamation mark, it will know to do that. So you saves you a lot of time with typing. And you'll see we get that problem right. See, it gives you what that is. If you did 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1, you will get 362,880. This is the same thing here. This says there are 9 books on a shelf, and how many ways can you arrange the books on your shelf? Pick any one of the 9 books, then any one of the 8 books. It's exact same number. So it's going to be 9 factorial. I was just lucky I got the same numbers, but you can see it's the exact same type of problem. On problem 8, it says, suppose a designer has a palette of 8 colors to work with and wants to design a flag with 2 vertical stripes, all of different colors. How many possible flags can be created? Okay, so let's take a look at this. We got 8 colors. You can label them if you want. A, B, C, D, E, F, G, H. There's my 8 different colors. So now we need 2 vertical stripes. And so were they designing a flag, right? So like, for example, maybe you're designing a flag with 2 vertical stripes, and you have these 8 colors to choose from. Let's say one of them is red, and you make this first one red, and you make this second one, let's say you make the second one yellow or something here. So here's a second vertical stripe, and you make it yellow. Okay, so that's what we're doing here. So how many colors do you have to choose from to start off with? 8. And does it say they have to be different? Yes, it does. 2 vertical stripes, all of different color, or both of different color, however you like to say it. So that's 8. Now this has to be a different color. So how many choices are there? 7. But there's something that matters here. And that is, for example, let's say that you have a flag that looks like this. The first vertical stripe is red and the second one is yellow. Well, guess what? You could have another flag with 2 vertical stripes with the same colors, but in a different order. For example, the first one might be yellow and the second one be red. So order matters here. This is a different flag than the one shown above here. So since order matters, there's 2 different ways that you could arrange these 2 colors here. So we have to multiply this by 2 because there are 2 arrangements of color. So really the answer to this is, where I'll just type it in like this, 8 times 7 times 2. A little tricky there with that 2. Let me see here. 8 colors and wants to design a flag with 2 vertical stripes, all of different colors. How many possible flags can be created? Wow, I'm surprised I didn't get this here. Let's see. I'm going to take a look at the written example here and see why we missed it. This is 3 vertical. Okay. I guess they're not looking at the 2 arrangements of the colors on this. I would think they would. Yeah, they're not looking at that. So 8 colors to work with and design a flag with 2 vertical stripes. I don't see why it wouldn't matter on that problem. So I'm not sure why they're not multiplying it by 2. Maybe I'm not sure of the design on this. I probably would have to look at this video, but for some reason they're not looking at the colors being in different positions. And I would think it would matter. So I'll take a look at that one, and I'll take a look at the video too, so we can double check that one. So a lot of these are getting similar. I think this class, I forget if this class ends at 6:30 or if it ends at 6, to tell you the truth. So I'll keep going with these, and we can even go back to the other ones. So with this one, it says on 9, it says you pick four digits at random without replacement. So you can't pick the same number twice, is what that means, without replacement, and write them in the order picked. What is the probability that you have written the first 4 digits of your phone number? So on this, the first 4 digits of your phone number, there's only one arrangement of that. Okay, so your phone number, that's only one set of 4 numbers there. You know, maybe it's 8763 or something like that. So there's a set number right there. And so now, how many different choices do you have to get these? So the first digits, here's the first 4 digits. So this is back to accounting of these things. So the first digit, there's 10 possibilities. Now this says at random without, here's the key thing, without replacement. So you're picking 4 digits at random without replacement. So you can pick the 0, you could pick the 9, you can pick the 1, but you can't pick it again. So that means that there's only 9 choices here, 8 choices here, or 7 choices here. So the probability that your number is this number is 1 out of that, out of 10 times 9 times 8 times 7. This is all the different possibilities that you could guess. Like you could guess that is the last digit 4 digits, is it 1, 2, 3, 7? No, it's not. These are the 4 digits that I'm looking for. So how many possible things could you guess? This many, 10 times 9 times 8 times 7. How many of them are right? There's only one choice that's right, whatever your 4 digits are on your phone number. There's only one of those group of 4 digits that are right. So the right answer there, and it has to be written in the form of a fraction, is 1 over that fraction, 10 times 9 times 8 times 7. Okie doke. So just read through these as you do them. Use your written examples and the videos to help you, and then practice them. So on 10, it says a pianist is to play 4 pieces for recital from her repertoire of 23 pieces. How many different recital programs are possible? So what this means is she has 23 options. Now, she's not going to play the same song twice, but she's going to play 4 songs. So she has 23 options for her first song that she plays. She's not going to play that song again. She's not going to play Beethoven's Fifth and then play Beethoven's Fifth again. So she has 22 choices for the next, then 21, and then 20. And you just multiply those together. And that's all you do with that problem. So that's similar to many of them that we already did. And also check to see if it says probability in there. Like the previous one said probability, so that was 1 out of that total. This doesn't say what's the probability that she played item number 1, then item number 23, or anything like that. So it's just that right there. If we go to problem 11 here, it says, how many ways can we select 3 door prizes? So we're looking to select 3 door prizes from 6 different ones. So we got 6 possible door prizes. And we're selecting out 3 of them. And we're distributing them among 3 people. Okay, so that really isn't needed. It's just once we get these, we're giving them to 3 people. So person 1 here gets any one of the 6 door prizes. Once that's given away, we're down to 5 door prizes for this person to get. And then this person can get any of the remaining 4. So it's just that right there. Just 6 times 5 times 4, which is 120. And I think there's only one problem left here. And this one, that was problem number 11. And problem number 12 says you got 7 sprinters have made it to the Olympics finals. So we got 7 sprinters. So have made it to the Olympic finals in the 100-meter race. And how many different ways can the top 4 occur? So we got 7 sprinters. Now, any one of them can come in 7th, 6th, 5th, 4th, 3rd, 2nd, and 1st. But we're only interested in the top 4. So any one of these 7 can come in 1st place. Then after that person comes in 1st, then any one of the 6 can come in 2nd. And after that, any one of the 5 can come in 3rd. And after that, any of one of the 4 remaining could come in 3rd. And again, it's just multiplying these together. And I think I'll just type it in this way. 7 times 6, 5 times 4. And that would be that one. So there were a couple tough ones. These previous ones were not that tough, but we did have a couple tough ones in there. So that's, I think this second section on counting techniques, when you look at the written examples in that, will help you out a good bit. So that, I think it's an easier section than the first section that we did, which was the compound probability that we did. So any questions that the folks have? Did you want to see other problems or from these? Anybody wants to see additional problems or have any questions? And if you stick around, Wendy, I'll check the grade book and we'll look around and see about the teaching presentation.
Okay.
Other questions? Anybody have any other questions at all? Or did you want to see any other problems from this section here? What I would do again is don't wait too long to get on them. Yeah.
I think I do. So I'm looking at my question 11 for counting techniques. And
Okay.
it says, how many ways can we select 3 door prizes from 9 different ones and distribute them among 3 people?
So you have 9 different door prizes and you're distributing them to how many people? 3?
Yes.
So that would be, this is how I would draw that up, 9 choices. So this first person here, this person that gets the first door prizes, he has a choice of 9 door prizes that you have. Then once that door, okay with that so far?
Yeah, it had tripped me up because my number was bigger than yours.
Yeah.
But now I do.
You got it? Okay.
Yeah.
Yeah. Okay. All right. And then, like I was saying, some of these compound probability, they're probably the hardest ones, that there was ones on there that were pretty tough. We did at least one of each type, but there were some that were tough. And I forget where they really showed up the most. But we can look at any of these you want to look at, if you want to look at any ones that we didn't do or ones we did. we can go back and look at them since we have time, plenty of time to do those. So anybody else have any questions? If you don't have questions, then just stay up on the dates that things are due. You can see right there on the calendar that one of these homework assignments is due Friday. It does take a while if you haven't, I've done these problems a lot. And so but it's going to take you a longer time to get through them. So make sure if you got spare time tonight, tomorrow, whatever, don't wait till Friday to do them. If you have time, get started on them. Don't wait till Sunday to do the second one. Yep. So if you have questions, go ahead.
Can we do compound probability, question 17?
Yeah. So let's take a look at that. So up to problem 17. So this one was a problem that was written to deal with social justice issues. So let's go ahead and do that. And it deals with probability and that sort of thing. So here on problem number 17, this is back on the compound probability. It says, again, this question is not on a test because it takes too long to do, but it is on the homework assignment. So it says the table below shows the number of people for 3 different race groups who were shot by police that were either armed or unarmed. And, that was a big thing in the news, and it still is. So these values are very close to the exact numbers. And in fact, I have a Excel sheet on, gives the name of everybody that was shot and killed by police over the last 4 years or so, and whether they were armed or not armed. And it gives a whole bunch of data on that. But this one changes one of the random numbers, but these are very close to the actual values. And this was from, I think, 2015 to 2018 or so, those 3 years. So it's that time period. But anyway, they have been changed slightly for each student to get a different number. So it says, give your answer as a decimal to at least 3 decimal places. So what percent are Black? So in this table of people that were shot and killed by the police, what percent are Black? So you can see that there's 624. So I'll type in 624 out of a total of 2307. And then what percent are unarmed? Well, total number of people unarmed is 162. So that'd be 162 out of the total 2307. Okay, so it says, in order for 2 variables to be independent of each other, then the probability of A and B is equal to the probability of A times probability of B. Now, independent means that one thing doesn't affect the other. In other words, on this, if these are independent, then if I multiply these 2 percentages, these 2 fractions together, I should get the probability of Black and unarmed. But it won't occur here because these things are not independent of each other. So, okay, this just means that the percentage of times that both things happen equals the individual percentages multiplied together. Only if they are independent of each other, okay? So there was no blank to fill in there. It's just kind of giving you a definition of what it means to be independent. See, one coin is independent of another coin. It doesn't matter what the coin does. So here, going through this says, therefore, if a person's race is independent of whether they were killed being unarmed, then the percentage of Blacks people that are killed while being unarmed should equal the percentage of Blacks times the percentage of unarmed. Let's check this. Multiply your answer to part A times your answer to part B. So right here, we can just do this right here. We can do 624 out of 2307. And then I'll say times 162 out of 2307. Now, unfortunately, it doesn't give me a approximation for that percentage, but I do have a calculator open here. Let me see if I can do this on a calculator. So, oh, it's a mess here on this calculator. Maybe somebody has a better calculator. Right now, my calculator isn't working, but it'd be 624 divided by 2307. So that's this number right there. And then what I'll do to finish it off, I'll multiply it by this fraction right here. So I'll say times the 162 divided by the 2307. 2307. So you can see we get something like this, 0.0189. So that value there of these two fractions multiplied together, if you like it as a decimal, is 0.01899. It's about 1.9%. So, okay, remember this is only correct up here if they're independent. Now let's get the real percent that are black and unarmed using the table. So now we want the percent that are black and unarmed. So that would be black and unarmed is 64. So that'd be 64 out of the entire table, 2307. Okay. Now, are these two things equal to each other? So you can see right here, if they were independent of each other, it should be in terms of percentage, it would be a 1.899%. 1.899%. But the real answer is 64 out of 2307. So let me do that. 64 out of 2307. And that is about twice as high. See, this is about 2.77%. So that means that they're not independent of each other. That means that your race does affect whether you're going to be shot and killed by the police while being unarmed. And so now what we're doing down here is let's compare the percentage of unarmed shot for each race. What percent are white and unarmed? Well, let's get that. White and unarmed would be, let's see, that would be 68 out of 2307. 68 out of 2307. Okay, so hold on here a second. White and unarmed, let me make sure here, got to scroll up. 68 out of 2307. What percent are Hispanic and unarmed? Okay, let's get that one. Hispanic and unarmed is right here. That's 30 out of 2307. 30 out of 2307. And now it says, if you compare answers D, E, and F, it shows the highest percentage of unarmed people being shot is most likely white. Why is that? This is because there are more white people in the United States than there are of any other race. And therefore, there are likely to be more white people on the table. Since there are more white people on the table, there most likely would be more white and unarmed people shot by the police. There would also be more white and armed people shot by the police than any other race. All percentage of white people would be higher than any other race because there are more white people on the table. For example, the table contains very few Hispanic people, and the percentage of people in the table that were Hispanic and unarmed is the lowest. And, just rolling on here, think of it this way. If you went to a college that was 90% female and 10% male, then females would most likely have the highest percentage of A grades. They would also most likely have the highest percentage of B, C, D, and F grades. The correct way to compare is conditional probability. Conditional probability is getting the probability of something happening given we are dealing with just the people in that particular group. So now in G, we're doing what percent of blacks shot and killed by the police were unarmed? Okay, what percentage of blacks? So how many blacks are we dealing with here in this table? 624. So let me type in the fraction here. And the bottom is 624. And how many of them were shot and killed by the police? So of that 624 up here, how many were unarmed, I think is what it's saying here. What percentage of blacks shot and killed by the police were unarmed? So 624 were shot and killed by the police. And of that 624, 64 were unarmed. So this is 64 out of 624. And this is definitely bigger than 10%. what percentage of whites were killed by, what percent of whites shot and killed by police were unarmed? So this is out of white folks here, and it was 1256. So out of the, and I'll put in the bottom number is 1256. So you can see there's like twice as many white folks in this table as there are black folks in the table. But are there twice as many white folks that were unarmed? Well, of the 1,256 white folks that were killed by the police, 68 were unarmed. Now, this is where you see the difference. So if you look at this percentage, if you use the calculator, you would find out, or here, I'll do this over here. If you do 64 divided by 624, then I got, see, like I say, about 10%. So 10% of the black folks that are killed by police were unarmed. If we do this for the white folks with this fraction here, that would be 68 divided by the 1256, and that gives you 0.054, which is about 5%. And you can do the same thing with the Hispanics right here. But my point is, you can see that the answers to part G and H, that the percent of blacks that were unarmed and killed by the police is approximately twice that of the whites killed by police. And then you're supposed to say in here, why do you believe this is happening? So on this part, you do a little search on the internet for reasons why blacks are more likely to be killed by police. And I think you probably know of some reasons, but it's still, I kind of wanted you to cite a credible site on this, and just read this and you can see what you're supposed to put in there. Like, go to a site that talks about this issue and put a little bit of stuff in there about that. So I don't know for sure who asked this problem. Was it Wendy or
Paris.
Paris? What do you think, Paris? You okay with that one?
Yes. I think I got a little nervous of how many parts it was.
Yeah, it's too long to
I
put
was
on
like,
a
let
test.
me check for this.
Yeah, or why what now?
I said that's why I was like, let me ask for help, because I know for me it's frustrating to get things wrong and you have multiple parts to it.
Right.
So it's like,
Right.
Okay.
So yeah, this is a very long problem, but it is not on a test. So it's a homework problem that won't come up again. But it's it might be worth more than 1 point, but let me see. Does it say? Yeah, it's only worth 1 point. So, it's a long, long problem. But you know what? Some of those problems with the sodas and stuff like that, or the M&Ms, they take a good while to do too, and they're only worth 1 point. But this one's just, this is more of a, it's too long for a test. And I think the one before that is also not on the test, because this one, I can do this one too if you'd like to see this one. All you have to do with this one is, let me go ahead and do some of it. This one, you can subtract and get the percentages that you're dealing with. Like, for example, this is the same thing, but you have to make the table up. So look, you have a total of, this is the same situation, I think, about different race groups, how many are shot and killed by the police, and of them, how many are armed or unarmed. And so look, if you got 630 total blacks in this table and 570 were armed, then you just have to subtract. So right here, you could do 630, or you could use a calculator and do it, either way, minus the 570. And you can do the same thing here. And then to get the percent that were unarmed, we would take, let me just do this on if you do this on a calculator, that's 630 minus 570, you would get 60. It might just be easier to put that in. Now to get this percent, we would take the 60 divided by the 630. So over here, I'll just do 60 divided by the total, 630. And I get this. And then once it looks, see the percent sign? So we got to move our decimal point over 2 places. So this would be 9.5%. Now this is not the exact value. The other table was much closer to being the real numbers. But I tried to get this, when I did the random numbers in here, I tried to make them close to 10%, this one close to 5%, because that is what the real numbers are. So you would do the same thing here. And then it gets a little tricky down in this area. So you're like, how do I get these? Well, this one you can get by, if you know the total here, you can take these two, add them up, and subtract from this to get this value. Then you might say, well, how do I get this one? Well, you'll know these two, but the way you get this value right here is you know this percentage of the total were unarmed. So to get this, you switch that percent to a decimal, which would be 0.07, and don't round this too much, 99689 or so, times that total, 2576. Do that on a calculator, and that tells you how many are right there. I'll show you that right here. So if I would take that, see, I took that percentage, switched it to a decimal, multiplied by the total, and that tells me the number of unarmed. So if I would take the point, and it will be very close to the whole number here, 0.7996894, and that's a little bit of an approximation, times that 2576, I get, boom, 205.9999999. Now, the reason it doesn't say 206 is because I rounded this number right here. So the right number is 206 right in this area. So this is 206. And now that this is 206, you can get this by subtracting. I'll just take the total amount, the 2576, and subtract off the 206. And that means 2307 were unarmed. We're armed, 2370. And by the way, on this, with the Excel sheet I have that gives you the real data, some people are armed with a writing pen. That counts as being armed. So when people say they were armed, don't think that that means a gun. It could be a screwdriver, it could be a knife, could be a pen, could be a baseball bat, and a whole bunch of other things that a taser would be easier to handle. And then see, now you can get all these things in here by subtracting. See, do a little subtraction there. Okay, so any other ones that anybody wanted to see? Okay, well, I'll stop there unless anybody has any other questions. And but you can stick on if you want to. But Wendy, you wanted me to check out your stuff, right?
Yes, please.
Okay, so let me check this out. So I'm pulling this off the side so nobody sees your grade or anything like that. So hold on a second. I'm trying to get up to the top on this thing. Okay. And actually, I may still be recording, so let me stop the share and stop the record.